Greetings, this paper presents GraspCaps, a novel architecture based on Capsule Networks for generating per 0.6D grasp configurations for familiar objects. Despite the evident potential, research on the application of Capsule Networks for object grasping is notably lacking. This pioneering work aims to bridge this gap by exploring the unique strengths of Capsule Networks in the context of familiar object grasping. Key reasons to choose Capsule Networks for object grasping include: Capsule networks excel in capturing spatial hierarchies and part-whole relationships. They are geometric invariants and are robust against scale, orientation, and position variations. Moreover, capsule networks employ dynamic routing mechanisms instead of pooling, allowing for more flexible information flow between layers of the network. The GraspCaps architecture consists of three main modules: the feature extraction module, the capsule module, and the grasp synthesis module. The feature extraction module takes a normalized 1024 x 3-point cloud as its input and processes the point cloud using the feature extraction module from the dynamic graph CNN, DGCNN, to generate a 1024 x one-dimensional feature vector. DGCNN was chosen for this module due to its ability to capture both local and global context, handle permutation invariance, adapt to irregular sampling, and efficiently learn local structures. Specifically, it processes a point cloud by use of 4 edge conveyors. An edge conveyor first transforms the point cloud into n undirected local graphs of k nodes, where n is the number of points in the input point cloud, and k is an integer representing the number of closest neighboring points that are used for constructing the local graph. The network then applies a shared multi-layer perceptron, MLP, on the edges of the graphs. This process is repeated for each of the 4 edge conveyors in the feature extraction module. The output of all the edge conveyors is concatenated and processed using a shared MLP and pooled to a 1024 x 1 feature vector using an adaptive max pool operation. The capsule module is a crucial component of the network, comprising 3 layers: a fully connected layer, a primary capsule layer, and a secondary capsule layer. Each layer plays a distinct role in processing and classifying objects. The fully connected layer transforms the input feature vector, while the primary capsule layer extracts initial object features. The secondary capsule layer, with its deeper capsules, encodes more meaningful and refined object representations. The network ensures that each capsule in the deepest layer corresponds to a distinct object class. The object class is determined by ranking the activation norms of the secondary capsules. The capsule with the highest norm, the winner, provides the input for further processing, while the activations of other capsules are masked off. The grasping module consists of 4 fully connected heads. The first 2 layers consist of 512 and 1024 neurons respectively, using leaky ReLU activation. The third layer size is dependent on the output shape of the network and uses linear activation. The reconstruction head has an output shape of 1024 x 3 to generate point locations in 3D space. The grasp head has an output shape of 1024 x 4 to generate quaternion rotation vectors for each point. The quality and width heads both have an output shape of 1024 x 1, as they only need to output a scalar per point. The output of the grasping head is normalized to obtain a unit quaternion vector. Given the nature of our network, which entails simultaneous familiar object recognition and grasping on a point cloud, no existing benchmark datasets were identified that met our criteria. Therefore, we generate our own dataset to train and evaluate the proposed approach. We used 90 simulated household objects to generate a large synthetic object grasp dataset. Furthermore, to address the familiar object recognition task, we grouped all objects into 8 distinct object categories based on shape similarities. Similarly, we generate a real dataset to evaluate the performance of our approach in real-world settings. Note that for real-world experiments, we first train the network on synthetic objects and then fine-tune on real objects to enhance its performance. For each partial view of an object, 120 grasp configurations have been generated. These grasp points are centered on random points distributed uniformly within the point cloud of the object. We ensured that our datasets did not become biased towards the classes with a large number of objects such as the box class. The obtained synthetic dataset consists of 4,576 point cloud data, with 572 samples per class. In the case of the real object dataset, we captured 220 unique point clouds of 22 objects, and for each point cloud we generated approximately 120 grasp configurations, and in total 26,643 grasp configurations. In both real and synthetic datasets, we considered 70% of the available data for the training, and the remaining 30% for the validation. We observed that When tested on the real object dataset, our approach demonstrated a 95% grasp accuracy, whereas the baseline network converged to a significantly lower accuracy of 89%. Similarly, on the synthetic dataset, the GraspCaps network outperformed the ablated network. Please refer to the paper for more details. We also performed several rounds of experiments to assess the performance of the robot in robotic grasping tasks. In particular, the robot is tasked with a multi-step process, starting with identifying the class of the object in its vicinity. Subsequently, the architecture generates a grasp configuration for picking the object. The robot then executes the grasp, lifting the object and placing it into the basket. The performance of the robot is quantified through the computation of a success rate, defined as the number of successful grasps divided by the total number of attempts. In this example, a bottle object is placed in front of the robot. The top left image shows what the robot perceives through its camera. The top right visualizes the raw output of the fitness head of the GraspCaps network for the object, pointwise grasp quality, and the lower right images depicts the output when smoothed using our Gaussian filter. We randomly present 10 objects from each of the classes and instruct the robot to perform the pick and place scenario. We repeated this scenario several times to get a clear indication of the performance of the proposed networks and the baseline method. We found that, although both the GraspCaps network and the ablated network achieved a similar classification performance, the GraspCaps network outperformed the ablated network by a large margin in terms of grasping success. We also observed that most of the failure cases were with the cutlery class. The network consistently assigned the cutlery objects to the category of vertical objects. Cutlery items are characterized by their thin profile, often resulting in a point cloud containing fewer than 500 points. The visibility of these objects varies based on their pose relative to the camera and self-occlusion. We therefore upsample the point cloud of the object to reach the required 1024 points. However, this process introduced changes to the object's shape. In some instances, this transformation made the object more closely resemble a vertical cylinder, contributing to confusion in the classification process and explaining the observed poor grasping performance. This video shows the simulation of the pick and place task for various isolated objects. The GraspCaps network is shown to perform accurately and reliably. To assess the generalizability of the network, we conducted similar pick and place tests on a set of 15 novel objects retrieved from the 3GEMS dataset and Gazebo repository. This set of novel objects is shown in the center of the figure, and the way that the robot grasped each of these objects are shown in other tile images. Results of grasping novel objects experiments for GraspCaps and the baseline networks. When comparing the results of the GraspCaps network with the baseline network, it can be seen that the GraspCaps network outperforms the baseline network with an average of 90.7% grasping accuracy for the GraspCaps architecture compared to an average of 74.7% for the baseline network. We observe that for familiar classes like clock and T-box, both baseline and GraspCaps perform well with 90% success rate. However, for unfamiliar classes, for example, laptop, donut, camera, vase, etc., the part-whole properties inherent in capsule networks enable GraspCaps to outperform the baseline approach. We observed that most of the failures were mainly due to predicting the grasp point near the edge of an object. As the gripper initiated the closing motion, the object's position could be affected, leading to potential displacement. In this set of experiments, we conducted pick and place tasks using a real dual-arm robot to assess the effectiveness of the proposed approach in both isolated objects and pile of objects scenarios. In the isolated object scenarios, the GraspCaps network consistently exhibited accurate and reliable performance, efficiently grasping objects and placing them into the basket in the majority of trials. The successful execution of pick and place tasks in this setting demonstrates the network's adaptability to generalize to novel objects. The study identified that predicting grasp points near the edge of an object was a primary cause of grasping failures. Grasp point inaccuracy was compounded by camera robot calibration errors, hindering the robot's ability to successfully grasp the target object. While addressing grasp point refinement was beyond the scope of this work, existing literature has explored these challenges. In the pile of objects scenario, 5 objects were placed with random rotations and significant overlap on top of each other, resulting in some objects being partially or fully obscured from view. The GraspCaps network demonstrated good performance in handling such cases. Despite the challenges posed by obscured views, the robot successfully grasped objects from the pile and dropped them into the basket. This experiment showed that GraspCaps does not rely on pre-segmented point clouds and can handle complex scenarios with multiple objects and occlusions. Thank you for watching.